Today we'll be talking about gravitation, specifically Newton's law of universal gravity, gravitationally stored potential energy, Kepler's laws, orbital speed, and escape velocity. From our universal gravity simulation on PhET, we were able to look at how the mass of two objects and their center-to-center separation affects the magnitude of the gravitational interaction between them. After collecting data, we were able to see that the magnitude of the gravitational interaction between the two masses is directly proportional to the mass of mass 1, mass 2, and the inverse square of the center-to-center separation of each mass. Putting all those things together, we have that Newton's law of universal gravity, where g is the universal gravity constant that's equal to 6.67 times 10 to the negative 11, with units of newtons times meters squared, all divided by kilograms squared. One important thing to note about this equation is that this is not entirely different from our usual force of gravity equation. It's just that the force of gravity equation we have been using is specific only to problems that take place near the Earth's surface. If we isolate the mass of this object, or m2, we see that the coefficient that remains must be what we call g, or the strength of the Earth's gravitational field, 9.8 newtons per kilogram. Notice that you can pretty much find the gravitational field created by the presence of a large mass by swapping out the mass and radius of the Earth with the mass and radius of any other planet. Now, we've always had this idea of gravitationally stored potential energy, and thus far we've been doing energy problems that are zoomed in and occur near the surface of the Earth. But that's not to say that we cannot do this at the planetary limit just by zooming out. Since gravity is a conservative force, we can obtain an expression for a change in stored potential energy between 2 points due to working. Here we derive an expression for the working required to raise an object an infinitely far distance away from the Earth's surface, r. We can use our integral, which relates working to a conservative force. Since the force of gravity points in the opposite direction that the object is being lifted, then theta is 180 degrees, and then it gets a minus sign after we perform that dot product. We'll substitute our expression for force of gravity. Pulling out our constants, we get a cleaner integral to work with and just integrate with the power rule. Evaluating from r, where our object starts, to infinity, we get this difference here. Notice that if the denominator of a fraction is huge, the fraction gets smaller, and if the denominator is infinitely huge, like we have here, then that fraction is 0. And we have an expression for the working required to lift an object from the surface of the Earth, r, to infinitely far away. But since a change in gravitational potential energy of a system is equal to the negative working done by gravity on an object, we have this expression. Swapping out our specific big R with a small r to generalize for all distances between the surface of the Earth and infinity, we have an expression for the gravitationally stored potential energy of an object of mass m, a distance r from another object of mass big M. But what's going on with that minus sign? Like, what does negative energy actually mean? The thing that we need to take note of is that our math has to obey what we observe and what we expect at specific places. Here we know that if we have an object at rest far away from Earth, it has the most gravitationally stored potential energy and 0 kinetically stored energy. If you release it, it will plummet towards the Earth, where we'll have less gravitationally stored potential energy and more kinetically stored energy. Here, our boundaries are the center of the Earth, the surface of the Earth, its radius, and r equals infinity. We know that infinitely far away, gravitationally stored energy in the object Earth system must be 0 because the math says so. Anything divided by infinity must be 0. However, it must also be true that if we get closer to the planet than infinity, then the system has to have less gravitationally stored potential energy because it's then stored in the object kinetically. The red curve below shows the shape of the gravitationally stored potential energy function right here. The only way we can have less than zero is to have negative potential energy. Now, at the surface of the Earth, take note of the shape of the graph. It immediately changes. It becomes linear. We know that at the center of the Earth boundary, there's no more mass, so there cannot be a gravitational field, and therefore there cannot be any gravitationally stored energy in the system. The shape of the graph is linear, and that has to do with the fact that as you get closer and closer to the Earth, you have less and less mass between the center of the Earth and wherever little r is. That's between 0 and the radius of the Earth. In this section of the video, we'll be talking about Kepler's laws. While I don't particularly care about who Kepler is, we get to see how some of the things we just talked about can apply to solving problems. There's not too much to this first one. The first thing he concluded when studying the planets of our solar system is that the orbits are actually elliptical. He figured this out by looking at the sky a lot and noticing things about where Mars was at certain times of the year. Kepler's second law states that a line that connects a planet to the sun sweeps out equal areas in the plane of the planet's orbit in equal time intervals. In other words, the rate dA dt at which it sweeps out an area A has to remain constant. In the picture below, you see how Earth can sweep out a differently shaped triangle in 1 month during one time of the year when compared to another month at another time of the year. The areas of these two triangles have to be equal based on Kepler's second law. So here's the proof. Consider the fact that the planet-to-sun line will sweep out approximately a triangle for any period of time. The longer the time, the wider the triangle. Now, this triangle will have a height of r, and the base is that arc length s, which we say is r times the angle theta. When we combine our r's, we have an expression for the area of these triangles. It's 1/2 r squared delta theta. So now let's complete the proof. If we write this in differential form, we have dA and d theta on the other side. So when we take the time derivative of both sides, what happens is that we actually start to see something that looks familiar from a previously finished unit that we did in rotational kinematics. So that d theta dt we can actually then write as omega. So the thing about Kepler's second law is that it's actually a statement of conservation of angular momentum. Over here to the side, we can rewrite the angular momentum of this planet as r cross p. But that's really just r times p sine theta. And I'm going to open up the p and just have m times r times v sine theta. Now this sine theta here is what makes that v tangent to the path. So we can actually rewrite this as m times r v tangent to the orbit. And we can also rewrite this expression as m times r omega from rotational kinematics, and combining like terms, we have this expression L is equal to m r squared omega. Now, taking note on the left side, we do have an r squared omega, so when we swing over our m to do a substitution, what we have when we bring this over is that 1/2 L over m is equal to the time derivative of the area of this triangle. Now, since angular momentum is conserved and there's nothing changing about the mass of the planet, the term on the right-hand side is a constant, which means that as long as we're talking about the same period of time, that the area of those two triangles will be the same. When it comes to solving problems for the AP exam or your homework, one important part of this proof is seeing how the planets are being treated as point-like masses. So all of this stuff here with angular momentum is in play moving forward. Now in our problems, you'll see that for an ellipse, it's true that you might have different r's from whatever planet or satellite you're talking to its axis of rotation, but you'll see that planets will actually move slightly slower or faster based on where they are in their orbit, or specifically planets generally moving faster when they are close distance to the sun and slower when they are further away from the sun. Now, Kepler's third law states that the square of the period of any planet is proportional to the cube of the semi-major axis of its orbit. Here we note that the orbits of each planet, while ellipses, are really more like a circle than an oval. He actually came up with this in the same way we do our labs, with some linearizing. So, to make things short, what Kepler did here was he was able to calculate enough information to get the periods or the years for each planet, as well as their radii, and he plotted the radii cubed versus the periods squared, and he found out that this all came out to a straight line, which means that this number, these ratios, are all constant. We can prove Kepler's third law by approximating these orbits as circles and then using uniform circular motion. So what I'm going to do here is I'm going to swap out my net force for the net force of an object moving in a circle. And we see that we can cancel out a few things. So first thing I'm going to cancel out is the mass of the planet in question. And then we'll also see that the inverse r on the left side will cancel out one of the other inverse r's on the right side. Then I'm going to substitute in for v and say that the circumference of this quote-unquote circle divided by a year is equal to this speed, and I'm going to square it because the v had a squared with it. And on the right side, I'm just going to tidy things up and get that. So after I square everything on the left-hand side of the equation, I get my t squared coming out. And here we have our gravity constant, our big M, which is the mass of the sun in this case, and we also have our r. I'm going to move everything to the right except for our r's, which I will move to the left-hand side. So here is our r, and that's where the cube comes in. And over to the right, I have big G, big M, divided by 4 pi squared times the period squared. So this here in parentheses is that constant, or that slope of that line from the previous slide. So basically, if you knew the radii, or the average radii of each planet's orbits and the year on each planet, you could find a way to calculate the mass of the sun based on this expression here. The last part of this lecture is about the differences between orbital speed and escape velocity. Now I'm grouping these together, even though they don't have much to do with each other, is because their equations look extremely similar, and I would urge you to learn these simple derivations just so that you know which expression to use on the AP exam. The orbital speed is defined as the speed of a satellite or planet moving in a circular orbit. We can easily derive the orbital speed by using the net force equation and approximating to uniform circular motion. Plugging in our expression for centripetal force, we have on the left-hand side now mv squared over r again, just like how the last proof started. And I'm just going to rewrite this on the right-hand side. And we have the same things canceling out. No more m's, an inverse r goes away on the left, and we have one go away on the right. And we're now left with v squared is equal to the universal gravity constant, the mass of the sun, divided by the radius of orbit. And the only thing left to do now is to square root both sides. And we have an expression for the orbital speed of a planet or satellite moving in a circular orbit. Escape velocity, on the other hand, is the velocity required to launch something away from the planet so that it escapes the pull of that planet. Initially, let's say that the initial distance from the center of the planet is just r, while the final conditions require that we are infinitely far away and we have just enough velocity to escape. So we don't want any extra velocity, and we just want to make sure that we just get away from the pull of the planet. Now, deriving an expression for escape velocity is really just a matter of using the conservation of energy. In the initial conditions, we have, for the kinetic energy of this thing we are launching, we have 1/2 mass times its initial velocity squared. And an expression for the gravitationally stored potential energy in the system, which we will write with our new big G, big M, little m, divided by our initial. And that's equal to 1/2 mv final squared minus g m little m over the final distance. Now here, since the final distance is infinity, this term here goes away, because anything divided by infinity is 0 if you know your limits. And also we required no extra ek, or no extra velocity, so this expression here also becomes 0. Now, cleaning things up a little bit, I'm just going to move our initial eg term over to the right hand side by adding. So we have big G, big M, little m over r naught is equal to 1/2 mv initial squared. So finding the escape velocity, we can cross out these m's, these little m's on each side, and I'm just going to go ahead and swing over that 2. So here on the right hand side, I gain a 2 up top, big G, big M stay there, and now I have my r initial from the center of the Earth, and that's equal to the initial velocity squared. So finding the escape velocity, we have this expression after we square root. We have the square root of 2 big G, big M over the initial distance. So there's your expression for escape velocity. So notice how similar it looks to the expression we got in the last slide. The only difference between the two, and why I feel students mix these up, is that factor of root 2. So I can see how students might mix up one for the other. That's something you really don't want to do when you solve problems, and that's certainly something you don't want to do on a test or an AP exam. So I urge you to be able to please derive both of these from both uniform circular motion and energy conservation. And that's pretty much it for universal gravity. So I hope this helps, and I'll see you in class.